good evening. Thank you for watching my videos. So just this evening, I was studying my textbook, and it's talking about the stack. And what the stack is seems fairly straightforward, but I became a little stumped when it came to examining some sample assembly code. So I did the only thing that made sense to me, and that is, whenever I don't fully comprehend something, I solve the problem by creating a video to teach other people. Granted, that makes no sense. I'll get into it. I'll start examining that popular PIC 18 reference manual, and the link for that is below. It's almost 1,000 pages. But first, I will briefly discuss the stack and the stack pointer in the PIC 18. So to begin with, the stack is read-write memory in RAM. The stack is used by the CPU for temporarily storing critical information related to addressing in ROM, but I also gather that it doesn't just store addresses. I read somewhere that it can store data too. Well, maybe as I continue studying here, I'll have an answer for everyone. As I understand, the CPU needs this stack as storage area because generally there are a limited number of registers. That's according to a source I heard someone say. In the PIC 18, the stack is 21-bit, and the reason the stack is 21-bit is because the program counter is also 21-bit. I made a great video on the program counter. I'll leave a link for that below too, but you can find it on my channel. But anyway, this video I'm talking about the stack. The 21-bit stack is often used for the call instruction, and this is to make sure the PIC knows where to come back, particularly after the execution of a subroutine, or when the subroutine is called. I mentioned the 21-bit stack is the same size as the program counter. So, like the program counter, it can take the same address values, so from 0 to 2 megabytes. Okay, so if the stack is storing RAM, there must be a register in the CPU to point to it. And the pointer for this is called the stack pointer, or rather the SP register. So the register used to access the stack is called the stack pointer. In the case of the PIC 18, this stack pointer is 5-bit, and it can take values from 0, 0 to 1F in hexadecimal. This gives a total of 32 locations. That is 32 locations, and each of those locations is 21 bits wide. I read somewhere that upon power-up of the PIC, the SP register contains a value of 0, and thus stack location 1 is the first location used by the stack. The stack pointer points to the last location used. Stack location 0 is never available, and even when you look at the data sheets in the PIC 18, there are only 31 stack locations. So now I will try and explain what a push is. I'm speaking about how stacks are accessed in the PIC 18. So you may have heard this before. What is a push? When the CPU stores information such as the program counter on the stack, this is a push. The inverse is called a pop. This is when contents of the stack are popped back into a CPU register from the stack. So more differently, registers are pushed onto the stack to save them, and they are popped off the stack to regather them, to reclaim them. I mentioned already that the stack pointer points to the last used location of the stack. This last used location the stack pointer points to is called the top of the stack, or TOS for short. It is said that the stack pointer is incremented when data is pushed onto the stack. For every program counter that is saved on the stack pointer is incremented once. Popping is the opposite of pushing. When what is stored on the stack is brought back into a given register, likely the program counter, this is the opposite of pushing. This is called popping. The stack is LIFO, last in, first out memory. Hopefully that introduces the stack in the PIC-18. There are some specific instructions that affect the stack. They are the call instruction, return, rcall. So now I'm going to turn to the PIC-18 manual to try and gather all of the information related to the stack. And hopefully by the end of it, it makes sense. That's the goal of this video, is to make sense. It's important to have people take you seriously. 7.5 Stack. The stack allows a combination of up to 31 program calls and interrupts to occur. The stack contains the return address from the branch in program execution. Enhanced MCU devices have a 31-level deep x21-bit wide hardware stack. The stack space is not part of either program or data space, and the stack pointer is not readable or writable. The PC program counter is pushed onto the stack when a call instruction is executed or a file interrupt causes a branch. The stack is popped in the event of a return, retlw, or a retv instruction execution. The PC lat-h is not modified when the stack is pushed or popped. After the PC is pushed onto the stack 31 times without popping any values off the stack, the 30-second push overwrites the value from the 31st push and sets the STKFUL bit, while the STKPTR remains at 11111B. The 33rd push overwrites the 32nd push, and so on, while stackpeter remains 11111B. Stack pointer. When the stack overflow enable bit is enabled, a device reset will occur. Figure 7.5. Stack modification. Stack pointer, stack. Address 0, top of stack, and then the bottom of the stack is 11111. I looked it up. 5 ones in binary is number 31. Note 1. The stack pointer value does not increment past 31 in decimal, or that number in binary. Whenever the program branches, the return address is saved to the stack. Such branches include call, rcall, or an interrupt. The stack pointer is incremented and program counter 20:1 is pushed onto the return stack. PC0 is always assumed to be 0. When a branch return is executed, the top of the stack is popped to the program counter and the stack pointer is decremented. PC_lat_U and PC_lat_H are not affected during these branches. The program counter is word incremented by 2 after each instruction fetch during Q1 unless modified by a GOTO call, rcall, return, retlw, retfee, or branch instruction, modified by an interrupt response due to a write to PCL by an instruction. Skips are equivalent to a forced NOP cycle at the skipped address. Alright, so brace yourself for some intensely boring information. Sorry if that's offensive to all of the PIC nerds out there, but I'm going to read the reference manual. Sorry guys, I read and study so long that I get a little bit ridiculous sometimes. So forgive me if I hurt your feelings by calling you a PIC nerd. I guess that makes me a PIC nerd too. We're all nerds. We just have to accept it. Okay, I'll begin with the glossary at the end because it gives a basic definition of the stack. So the stack is a portion of the CPU that retains the return address for program execution. The stack gets loaded with the value in the program counter when a call instruction is executed or if an interrupt occurs. Here is the definition for push, a term used to refer to the action of saving information onto a stack, software and or hardware. And popped, that was the next thing. A term used to refer to the action of restoring information from a stack, software and or hardware. Hopefully I get to it, but there's the instruction set information at the end, which I believe will cover some of the instructions that deal with the stack, like call, retlw, retfee. So I read, I guess during the development of the PIC-12, a deeper hardware stack was a feature. The PIC-16s had an 8-level hardware stack, and the PIC-18 has a 32-level deep stack. I might want to pause and study this. Don't quite understand what it's saying, but anyway, there's a list of resets, stack overflow reset appearing in the list, and underflow reset as well. Okay, well, I'm learning as I'm reading. Figure 3.1, simplified block diagram of on-chip reset circuit. So here's a GLANS, like an OR gate, and there are different resets attached to it. So maybe when any of these reset, there'll be a reset. So maybe that's why it's an... Hold on. So here it just shows the stack pointer, stack overflow / underflow reset. So this is on the same subject of all these reset conditions, looking at RCON, register bits and positions. This is page 87, just to get a definition of this reset control register. The reset control RCON register contains flag bits to allow differentiation between resets. The reset control register has 7 bits. Well, here it is again. and one of the bits is unimplemented, so I guess that means it's 7 bits. I haven't quite understood this yet, but here's the stack full and stack underflow, so stack reset stuff. I won't comment on this, I don't understand it. That's why I won't comment. mclear resets, wdt reset, reset instruction, stack resets. Alright, I'll read this note. When the wake up, I'll start a new vid. Note 3, when the wake up is due to an interrupt and the GIEL or GIEH bit is set, the TOS, top of stack, U, top of stack H, and tossle are updated with the current value of the program counter. The stack pointer is modified to point to the next location in the hardware stack. Can't fully comprehend that, but anyway, I shouldn't comment. These 4 registers are applicable with that note I just read. So I looked at this in my program counter video, and this is where the level stack is in relation to the program counter, and this appears on page 94 in the General Enhanced MCU block diagram. I covered this instruction flow and pipelining content in my program counter video, and it's talking about the execution cycle as related to the program counter, but also the stack. So I won't cover it here. So here are the instructions, page 110, and then pop shows up. Pop top of return stack, TOS. Push top of return stack, TOS. Okay, so 5.3, talking about the central processing unit. I won't read it all, but the last sentence says, the CPU controls the program memory address bus, the data memory address bus, and accesses to the stack. In the memory organization section on page 131 of the PDF, the stack appears, but I already read this. But I didn't read this, and I might get to it. Return address stack. Okay, so this kind of introduces the section on memory in this manual. I won't read this, even though I just read it when I paused my video record here, but I will read this last sentence. In addition, there are other registers used that are neither part of the program nor data memory spaces. These registers are not directly addressable and include return address stack, fast return stack. I'm going to show my ignorance here, and maybe I have yet to find this out. Are we talking about the stack still, or is this something else? Don't hate me for not knowing. Don't be so judgmental. Just kidding. So I looked at this yesterday when I created my program counter video, so I won't cover this again. Here's the stack underneath the program counter, and it has a little arrow here going to other user memory spaces, which I guess is all of this. Okay, so this is familiar from yesterday's video on the program counter, and then it starts talking about the stack and the different situations. What is this again? Hold on. Okay, so this shows the 4 situations for loading of the program counter. And I guess situation 4, which I will show on screen in a moment, shows how the program counter is loaded during a call instruction with the program counter pushed onto the top of the stack. So I will scroll down to situation 4. So here is situation 4, which is a call instruction. Might want to pause and just read this, but it's got an arrow coming up from the program counter and going to the top of the stack. Situation 5 also shows access of the stack. See, all these other situations show the stack here, but in these situations the arrow for call points to the actual stack, and the rcall instruction and these retfee and retlw showing the arrow returning from the stack. The rcall instruction has two-way arrows going to and from the stack, but the return retfee or retlw instruction just has an arrow from the top of the stack back to the 21-bit register program counter. Well, I read some of this while I wasn't recording, and it's talking about the computed GOTO, and well, it mentions the stack. This is page 139. Okay, just scrolling through here. Page 142, the stack. Yeah, I already read this. It shows up on page 144, discussing the access bank. So I think we're still talking about the same thing here with the return address stack on page 147. So I will have to read all of this. The return address stack allows any combination of up to 31 program calls and interrupts to occur. The program counter is pushed onto the stack when a call or rcall instruction is executed or an interrupt is acknowledged. The program counter value is pulled off the stack on a return, retlw, or a retfee instruction. PC-lat-u and PC-lat-h are not affected by any of the return instructions. The stack operates as a 31-word by 21-bit RAM and a 5-bit stack pointer, with the stack pointer initialized to 0 after all resets. There is no RAM associated with stack pointer location 0. This is only a reset value. During a call type instruction causing a push onto the stack pointer is first incremented and the RAM location pointed to by the stack. I hit my microphone. During a call type instruction causing a push onto the stack pointer is first incremented and the RAM location pointed to by the stack pointer is written with the contents of the program counter. During a return type instruction causing a pop from the stack, the contents of the RAM location pointed to by the stack pointer register are transferred to the program counter, and then the stack pointer is decremented. The stack space is not part of either program or data space, and the stack pointer is neither readable nor writable. The address on the top of the stack is readable and writable through SFR registers. Data can also be pushed to or popped from the stack using the top of stack SFRs. Status bits indicate if the stack pointer attempts to exceed the 31 levels provided. The stack does not wrap when the stack is pushed greater than 31 times. So here's a diagram, figure 7.8. Return address stack and associated registers. Alright, forget where I was. Okay, return 7.8, return address stack and associated registers. Return address stack, TOSU, TOSH, TOSL, top of stack. Stack pointer 4. Top of stack access. The top of stack, TOS, is readable and writable. 3 register locations, TOSU, TOSH, and TOSL, hold the contents of the stack location pointed to by the stack pointer register. This allows users to implement a software stack if necessary. After a call, rcall, or interrupt, the software can read the pushed value by reading the TOSU, TOSH, and TOSL registers. These values can be placed on a user-defined software stack. At return time, the software can replace the TOSU, TOSH, and TOSL and do a return. The user must disable the global interrupt enable bits during this time to prevent inadvertent stack operations. Note, the user must disable interrupts when manipulating the stack. Page 148, push and pop instructions. Since the top of stack is readable and writable, the ability to push values onto the stack and pull values off the stack without disturbing normal program execution is a desirable option. To push the current program counter value onto the stack, a push instruction can be executed. This will increment the stack pointer and load the current program counter value onto the stack. TOSU, TOSH, and TOSL can then be modified to place data on the stack instead of a return address. This data may be a new return address. This may be done in the operation of a real-time operating system, RTOS. The ability to pull the TOS value off of the stack and replace it with the value that was previously pushed onto the stack without disturbing normal execution is achieved by using the pop instruction. The pop instruction discards the current TOS by decrementing the stack pointer. The previous value pushed onto the stack then becomes the TOS value. Example using the push instruction. Move LW, dummy TOSU, move WF, TOSU, move LW, and so on and so forth, using the pop instruction. Push, pop. Page 149. Return stack pointer. The stack pointer register contains the return stack pointer value and the overflow and underflow bits. The stack overflow bit, stack full, and underflow bit, stack unfull, allow software verification of a stack condition. The stack full and stack unfull bits are cleared only after a POR reset. After the program counter is pushed onto the stack 31 times without popping any values off the stack, the 30-second push overwrites the value from the 31st push and sets the stack full bit, while the stack pointer remains at 11111 the 33rd push overwrites the 32nd push, and so on, while stack pointer remains 11111. After the stack is popped enough times to unload the stack, the next pop will return a value of 0 to the program counter and set the stack unf bit while the stack pointer remains at 0. The next pop returns 0 again, and so on, while stack pointer remains 0. Note, returning a 0 to the program counter on an underflow has the effect of vectoring the program to the reset vector, where the stack conditions can be verified and appropriate actions can be taken. The stack pointer can be accessed through the stack pointer register. The user may read and write the stack pointer values. This can be used by a real-time operating system, RTOS, for return stack maintenance. Figure 7.8 shows the stack pointer register. The value of the stack pointer will be 0 through 31. At reset, the stack pointer value will be 0. The stack pointer will increment when pushing and will decrement when popping. Next, stack full/underflow resets. At the user's option, the overflow and underflow can cause a device reset to interrupt the program code. The reset is enabled with a configuration bit, STVREN. When the STVREN bit is disabled, a full of underflow condition will set the appropriate stack full or stack unf bit, but not cause a reset. When STVREN bit is enabled, a overflow or underflow will set the appropriate stack full or stack unf bit and then cause a device reset very similar in nature to the WDT reset. In either case, the stack full or stack unf bits are only cleared by user software or a POR reset. Fast register stack. A fast interrupt return action is available for interrupts. A fast return stack is provided for the status, WREG, and BSR registers and are only one in depth. The stack is neither readable nor writable and is loaded with the current value of the corresponding register when the processor vectors for an interrupt. Must have read that wrong. The values in the registers are then loaded back onto the working registers if the fast return instruction is used to return from the interrupt. Low or high priority interrupt pushes values into the stack registers. If both low and high priority interrupts are enabled, the stack registers cannot be used reliably for low priority interrupts. A high priority interrupt, if one occurs while servicing a low priority interrupt, will overwrite the stack registers stored by the low priority interrupt. If high priority interrupts are not disabled during low priority interrupts, users must save the key registers in software during a low priority interrupt. If no interrupts are used, the fast register stack can be used to restore the status, WREG, and BSR registers at the end of a subroutine call. To use the fast register stack for a subroutine call, a fast call instruction must be executed. I won't cover it, but the stack shows up in indirect addressing and file select registers on page 150 and 151. It shows up in interrupts, I'll just read this one paragraph. The return from interrupt instruction, retf, can be used to mark the end of the interrupt service routine. When the instruction is executed, the stack is popped and the GIE bit is set to whatever. It shows up on page 193, high priority interrupts. And it shows up a bunch of times here. Yeah, so it shows up all over the place for interrupts, which is a pretty lengthy section of the manual. This is page 633 under section 29 of the device configuration bits. This section itself starts at page 631, talking about configuration bits. On 633, the STVREN, what do we call it? Configuration bits? What are we calling it? Okay, 1 is a stack full. Underflow will cause reset. 0, stack full. Underflow will not cause reset. Here it is in this chart form. So I don't know, this is like configuration bits. And writing configuration bits. That's handy to know, page 637. And I guess, yeah, configuration bits. And then I guess you can configure Stack Overflow stuff. So this is page 657, section 31. I think I mentioned this at the beginning of my look at the manual here, where it talks about the different instructions. So the fast register stack shows up somewhere along the line here. Okay, so it's going to show up in the pop and push instructions, page 663. So now this is page 665 under this instruction set section, and is talking about instruction formats. And well, under this instruction description conventions, top of stack shows up. So that's how it can be. What is that? So these aren't instructions, they're like addresses for registers, like special function registers. So still on this same section, fast register stack. At times it is desirable to be able to quickly access and return from a function. This function may be called as a subroutine or an interrupt routine of the device. To reduce the overhead for access / returning from these functions, the architecture has the ability to save 3 key registers in a 1 deep register stack. These registers are WREG register, BSR bank select register, status register. The 2 events that cause these registers to be loaded onto the fast register stack are a fast call. I don't feel like reading this anymore. So yeah, I'm getting lazy. I don't feel like reading this, but page 706 elaborates on the call subroutine. So just pause the screen and have a little read. Page 750 talks about pop. 751 talks about push. You have to pause the screen and read it. Page 752, rcall. Yeah, retf is on page 756, but it doesn't mention the stack until like another page. retlw is on page 758. The return is on 760. This is page 883. On code development, I will read the stack depth. Stack depth. A counter can be implemented that is incremented in each function that is called and each time that the program counter is at an interrupt vector address. The counter is then decremented at the end of the function or interrupt service routine. The value of the stack can then be output to indicate if the stack depth is out of its normal range, minimum and maximum. It shows up on page 884. Page 885 talks about use of the high-level language like C and the stack. And in the glossary, I guess stack gets mentioned in the interrupt definition. Well, if you paused the screen and read everything that you were supposed to, that should cover everything that's in the reference manual regarding the stack. Well, thank you for listening, and sorry about my sarcasm a little bit. It's just hard to plow through information like this. So thank you very much for listening. I hope it's been helpful, and have a good day.
Hi, gorgeous lady. Are you single?
Well, I am now.
Sexy, baby, honey, yum yum. I quiver at your hot intensity.
Oh, Mr. Handsome, take me now.
We have to fight our passions. We just met.
You're right. Would you like to vacuum my car?
Oh, baby, yes, anything for you.